was a great. It's a great pleasure and great honor. So my name is Valentin Volkov. I'm from Russia. I'm director for the Center for Photonics and N2D Materials from MIPT. All the results that I'm going to present today, of course, appear due to the successful collaborations between several European, actually, and not only European universities. So before I start, I would like to acknowledge the contribution from all my collaborators. So we have a great collaboration with our Spanish colleagues. So it's a research group of Pablo Alonso Gonzalez, research group of Alexei Nikitin. Then, of course, I should mention the contribution from the research group of Sasha Grigorenko from Manchester University and Kostya Novoselov from Manchester and National University of Singapore. And then, of course, our Swedish colleagues, research group of Professor Timo. So I'm going to talk about anisotropic nanophotonics. And as everyone knows, anisotropy, it's a very important phenomena, plays crucial role in light manipulation. And this is all because of the differences phenomena. Owing basically, or it's all about doubling the incoming light into two different rays, which is traditionally called ordinary one and extraordinary. And this doubling actually results in a special and polarization separation and opens possibility for realization of a variety of different useful devices, components, including polarizers, wave plates, optical phase maintaining fibers, and many, many others. And the performance of all these great devices is primarily depends on basically phase difference between those ordinary and the extraordinary rays. And this depends on two characteristics, the thickness of the device and the befringes of the materials which the device consists of. So it's D and delta N. And then, of course, already from here, it's clear that delta N is a very important parameters because we would like to have our device as compact as possible and as efficient as possible as well. So, and unfortunately, despite the great importance of the, let's say, of the aforementioned phenomena, the currently used materials possess a quite small differences with a record value of only something around 0.8. And this is called a giant anisotropy, giant differences. The majority of the materials, they are much, much smaller than that. So, and of course, all this inspired an intensive search for giant optical anisotropy among natural and artificial materials. So before we actually jump to the experimental results, we will try to answer the natural questions, which is where one should look for giant befringes, or in other words, what is the general properties for highly anisotropic materials. And of course, first one should pay attention to the geometrical parameters of the crystal lattice or crystal structures, because it is well known that, for example, for photonic crystals, one can easily achieve nice and significant any actual anisotropy by playing with alternating layers of different materials of different refractive indices. So geometrical parameters are important for anisotropy. The second pass toward the befringes is, of course, atomic polarizability. Kind of intuitively, one can achieve, or one can at least expect to achieve large optical anisotropy by tuning or playing with a polarizability tensor, which basically requires the controlling the nature and distribution of the consistent elements of the lattice of the material. So therefore, we are going to look for materials which have both of those features. So they have geometrical anisotropy, and they have a high polarizability of the atoms. So, and simply out of that, one of the best candidates is for this role is recently raised family of so-called TMDC materials. So basically, they indeed satisfy both criteria. Their van der Waals nature give rise to geometrical anisotropy, and their ions polarizability is one of the highest among available ones. Now we know which materials to look for. The next question is how to do it, because the measurement or the measurements from of the anisotropic optical response from the TMDC crystal is a challenge itself because of some experimental issues, obstacles. And one of the hardest parts is the implementation of traditional diffraction limit techniques such as transmit and reflectance, microscopy, spectroscopy, ellipsometry measurements. And this is because of the size, geometrical size of the TMDC crystals, which, I mean, traditional crystals or flakes, which are the object of the investigation, they are obtained by exfoliation, so by use of so-called sticky tape approach. And as a result, those samples itself, they are only a few tenths of microns, from tens to hundreds of micrometers. So if you're lucky, basically. So there, the usage of diffraction limited techniques may actually face some difficulties to measure the response out of that. And the second difficulty is related to the measured signals low sensitivity of the out-of-plane components attributed to the very high in-plane refractive index of the crystal, which is typically around 4. Here, for example, one can see a typical ellipsometry measurements scheme where the light hit the TMDC crystal under the angle of 80 degrees. So the refraction angle under the Snell's law would be around 14 degrees, which means that the probed field mainly field the in-plane component of the dielectric constant and does not feel the out. So to overcome these difficulties, we actually performed so-called imaging spectroscopy, spectroscopic ellipsometry, which is a smart hybrid of ellipsometer and microscope. So it actually enables surface characterization with lateral resolution of up to 1 micron. So additionally, of course, we also measured our flakes with scattering near field optical microscopy, which is exactly very highly sensitive to dielectric, out of plane dielectric permittivity, unlike the far field techniques. So, and then of course, both these approaches, they are verified with first principle calculations to be sure that we are on the safe side. All the measurements which were done here, they were focused on MOS2 crystal, even though, of course, all the achievements, all the results, they are easily to be extended to other materials from TMDC. So here one can see a typical image obtained by our imaging ellipsometry. Already from here, one can see that we are simultaneously able to measure the signal from several areas of the flake, which actually improves the quality of the results that are achieved in there. So very important to keep in mind that all the flakes, they are placed on a standard silicon substrates, and the presence of this silicon dioxide substrates gives rise of interference beams for ordinary and extraordinary rays, resulting in a pronounced peak in the ellipsometry spectra. already, I mean, for our particular result, these peaks are obtained at the wavelengths around 850 nanometers. So already from the shape of this peak, it's clear that we are dealing with materials with the material which is characterized by a large differences. So we don't even need to do any additional modeling of the experimental curve. But nevertheless, of course, we done the standard procedure of fitting data obtained from the ellipsometry measurements. So, and the resulting dielectric function is presented on the slide. All the experimental results are found to be in a really great agreement with the results of our first principle calculations, which was a bit surprising, but nevertheless. So, and as compared to the befringes, one can clearly see that results obtained for our MOS2 flake are significantly higher than previous befringes champions like HBN, Bari TS3. So they're several times higher than that, and actually order of magnitude higher or bigger than the standard anisotropic materials used in optics. One should actually keep keep attention on absolute value of refractive index, especially for in-plane component. One can see that this value is on the same level as the high refractive index semiconductors traditionally used in photonics, such as silicon, gallium arsenide, and other. So from these results, it's also clear that it also explains our choice of MOS2 because molybdenum disulfide have one of the highest distance between layers and thus has the highest befringes among other TMDC materials. Even though, of course, it's clearly seen that other materials from the family, TMDC family, also demonstrate giant anisotropy as well. So then, of course, to validate the extracted dielectric functions, we analyzed the waveguide modes, which were excited along TMDC MOS2 flakes. So for this, we used near-field optical scanning, scattering near-field optical microscopy. Here one can see a typical topography and corresponding near-field optical image obtained at the wavelengths around 1530 nanometers. So one can clearly see the fringes, which is due to the reflection of the light from the edge of the flake. So the similar results were obtained in a very wide wavelength range, basically from visible up to 1630 nanometers. Then we used it to estimate the dispersion of the mode, and then these experimental results were actually overlapped with corresponding dispersion color map for isotropic and anisotropic model. So one can clearly see that indeed we are dealing with highly anisotropic materials, which are proved by the perfect agreement between theory and the experiment. So one should of course here to ask the question, what is, obviously we are dealing with strongly pronounced anisotropic phenomena, but this phenomena is, let's say, has out of plane nature. So which makes it, at least from the first glance, a bit difficult to be used for some practical applications, because one should probably think that for some practical devices, practical applications, one would prefer to have anisotropy in plane. And surprisingly, actually, there are some papers which proves that you can grow vertical layers of MOS2, even though, of course, those layers, they are not, let's say, ordered, and which kind of deteriorate the advantage of the anisotropy. So, advantage of this in-plane anisotropy. So one should keep in mind, or one should ask for a question: what would be the application for out-of-plane anisotropy? Is there a possibility that it can lead to interesting application in nanoscale photonics, which is also unattainable with traditional isotropic materials? And in this regard, the extreme skin depth, or briefly ESKI phenomena, actually epitomizes the importance of highly anisotropic materials for some practical photonic applications. This phenomena in general originates from the general law of total internal reflection. In a classical case, if the refractive index of one material is larger than another one, and then the incident light is greater than the critical one, then light is reflected in the first medium and decays in the second one. So, and this is a very important phenomenon, which is the core of the modern telecommunication technologies for guiding light at vast distances. The problem starts once you are trying to shrink the size of such a waveguide to the some wavelength dimension. Then, of course, the mode is squeezed out because it's totally diffraction limited. To this day, one of the best solutions to overcome this diffraction problem is to use a generalized form of total internal reflection at the interface between isotropic and actually anisotropic metamaterial, accepting the fact that the refractive index of the isotropic material is larger than out-of-plane component of the anisotropic. Contributively, of course, the in-plane components could have any value even higher than one for isotropic material. It's actually interesting that the greater the magnitude of this component, the better actually the light confinement inside the waveguide core, and the better or the closer to the diffraction limit you can actually approach in the mode confinement. And to experimentally demonstrate the evidence of this effect, we actually covered the surface from this interface for planar E-skid waveguide. So the measured dispersion, so we used scattering near field optical microscopy to characterize the efficiency of our waveguide, and the measured dispersion for the waveguide together with corresponding theoretical predictions are shown on this slide, and found to be in a really good agreement between theory and experiment. So here probably one should mention that MOS2 as anisotropic materials yields significantly better light confinement, even in comparison with artificial anisotropic metamaterials. And this, of course, opens a new concept of vertically integrated photonic circuits, which recently has been proven to be useful degree of freedom for efficient nanoscale light manipulation. So the results of this research can be found in more details in this paper, which has been recently published in Nature Communication. It's called Giant Optical Anisotropy in Transition Metal Dehalcogenates for Next Generation Nanophotonics. So I mentioned, what time do I have? Like 10 minutes, 5?
You have 15.
15 minutes. Okay, so then I have time for a few more slides. So I already mentioned the possibility of using highly anisotropic TMDC materials for guiding, for manipulation of guiding modes. But one can also use the same approach for creation of highly efficient anisotropic dielectric nanoresonators. So it's not only good, so TMDC materials are not only good as a universal nanophotonic platform for guiding of the light, but also for localization of the light. And here, of course, one should mention pioneering paper of Timur Shigai, which has been recently published in Nature Nanotechnology. They basically probably one of the first who demonstrated that one can use a standard lithographic approach to nanostructure TMDC flakes to produce small nanodiscs, which can be used as a high index dielectric Me nanoresonators. And we are kind of also working in this direction. Basically in our recent research, which has been done together with a group of Professor Fedyanin from the Moscow Institute of Moscow State University, we actually applied the same approach, lithography and etching technique, to fabricate, to single crystalline MOS2 flake, to fabricate array of nanodiscs that support magnetic dipole Me resonances in near infrared spectral range. So these nanodiscs were studied by second harmonic generation, rotational anisotropy, revealing the retention of crystallinity and orientation of crystallographic axis of the single disk structure after fabrication. So then, of course, we investigated the nature of these magnetic dipole resonances, and then it has been found that it manifestates as resonant intensity enhancement in second harmonic generation spectra. So we found that tuning Me resonances by selecting the geometrical size of the nanodisk, we managed to demonstrate a very strong enhancement of second harmonic signal due to the efficient overlap of the optical resonances at the fundamental wavelengths with C exciton resonance at the second harmonic wavelengths. Obviously, one can, it has already been shown that one can create a high refractive index anisotropic Me nanoresonator from TMDC, but what about a spherical one? To produce a sphere, it's a certain kind of a challenge, because you can't really use standard lithography approach, because this gives the way to produce a kind of a planar structure. So the spherical one, it's not easy to be produced with a lithography. And of course, it has been also shown in the Shigai paper that actually highly anisotropic sphere is a very interesting object for nanoresonator applications. So what we did, we actually provide, or we developed highly excitonic, high refractive index spherical nanoresonators fabrication by use of short impulse laser ablation. So that's the approach which we try to use to bridge this gap in the fabrication and to broaden an application scope of the TMDC nanomaterials. So basically, laser ablation is, so what is the laser ablation? It's a laser-based technique for natural production of, let's say, nanoclusters. So when one irradiate a target with focused laser beam, one can hit it, one can melt it, and then finally one can ablate it. And then the surface of the target will become a nanostructured and I mean, if we will do this process in air, then nanoclusters will fly away from the target, and then they could be deposited on some substrates. If you bring something close to the surface, one can also do it in liquid. Then these nanoclusters will form colloidal solutions. That's what we actually did in our experiments. It's interesting that technique was known for a long time, but basically only in the beginning of, I would say, 19th. It's 1990s. It's start to be used for the actually nanofabrication of some colloidal structures. So nevertheless, we used this approach. The experiments was done in a close collaboration with research group of Andrei Kabashin. He well known for the generation of nanostructures by use of laser ablation. He has a group in University of Marseille and also University of in MIFI. It's a Russian university. So we closely collaborated with both of his groups. So we, as a result, we managed to produce high quality spherical MOS2 nanoparticles. Here you can see some images of the fabricated structures. So we produce different colloidal solutions with the particles of different sizes, basically from few nanometers up from 5 nanometers up to hundreds of nanometers. So it has been found that these fabricated nanoresonators actually manage to preserve the crystallinity, at least especially the crystallinity which is inherent to the initial crystal. So for the bigger nanoresonators, it looks like polycrystalline core with fully ran-like shell. But the smaller the size of the sphere, the more structured it became. And then for the few nanometers, nanospheres, basically, that's anisotropic quantum dots, the resonators became highly structured and high quality multilayer, let's say, preserving the crystalline structure of the initial crystal. So the paper now submitted to Advanced Materials, and in a few days it will appear at the archive. So one will be able to basically see the details of this research soon. So we of course also did optical characterization and photothermal response investigations of these fabricated materials. It has been actually shown that again, nanoparticles preserve the inherent bulk optical characteristics. These optical characteristics, for example, shown to be superior to conventional materials like silicon or gallium P, for example. And additionally, our results actually managed to demonstrate a really significant improve in photoresponse and in photothermal response compared to traditional materials like silicon. So on this, I think I will finalize my talk. So in conclusion, we managed to demonstrate the giant anisotropy in layered TMDC materials. We showed that TMDC allows to achieve to open interesting possibility for manipulation of light at the nanoscale, to achieve basically the diffraction limit and I hope now I managed to convince you that this is a really interesting platform for next generation nanophotonics. So I would like to also acknowledge the contribution from my team, and thank you very much for your attention.
Thank you very much, Valentin, for the nice talk. And now the time for the questions. Do you have questions? No, one question in the audience.
Valentin, thank you very much for the nice talk. So my question, I'm wondering whether you have checked that with MDC in that frequency range fulfill the condition of the existence of diagonal waves. So when a material is anisotropic and all the components of the tensor are positive.
So sorry, I have problems with hearing you. Sorry. Would you please? I will try to.
Now.
Would you please repeat it?
Is it better now?
Yeah. It's slightly better. Yeah.
So from where do I start? The whole question. I repeat.
From the beginning, if possible.
I mean, did you check your materials TMDC for the existence of diagonal waves?
I think TMDC material. I mean, you are talking about exactly about TMDC materials like MOS2.
Yes, for example.
MOS2, I think it does not support diagonal waves. I think we did try to check it, but there are other. I mean, the family of TMDC materials is broad. I think we are now looking for those with more sophisticated crystal lattice, where one can actually expect to have diagonal waves. Yeah.
Oh, okay, so that would be nice to.
Yeah.
And I have a second question. Can you grow TMDC on top of, for example, metal nanoparticles, metal spherical nanoparticles?
Yes, that's another thing which we are. You mean to produce a hybrid?
Yes, because you need.
It seems like it's possible, but there might be a problem right now to control the exact structure of this composite. Yeah. So we are now working on in this direction as well. So one should expect some interesting results out of such a combination.
Okay, thank you very much for doing.
Yeah.
Let's thank our speaker again.
Thank you very much for your attention. Yeah.
And that's the time to move to the next speaker, Professor Ajit Srivastava, with the talk Interacting Excitons in van der Waals heterostructures. So, professors, stage is yours. Not yet. Wait a second. There is some technical issues.
Okay. All right. Sorry about that. Can everybody hear me?
Yes, we hear you.
Perfect. All right. So, and you can see my screen and the cursor as well.
Yes.
Perfect. All right. So I'll go ahead. First of all, I would like to thank the organizers for organizing this wonderful conference. Unfortunately, I can't be there in person, but yeah, next time. So today I'm going to talk about interacting excitons in van der Waals heterostructures. So before I begin, I would like to acknowledge the people who actually did this work. In particular, my student Vijay Lee and a former postdoc Shin, who's not at Tulane, and former postdoc Sudipta, who's at IIT Kanpur, and Xiaotong and Luca. Okay, so in our lab, we study light matter interactions in low dimensional materials. And the focus is typically on the quantum and quantum geometric and topological side. And everything is happening in a driven dissipative setting because we are dealing with optics. So the matter for us is always quantum. The light can be classical, or we can either look at or generate or probe with quantum light. Okay, so that's the kind of setting in our lab. What do we want to do? Broad theme is to understand how exotic matter could give you exotic light. So that could be useful for getting interesting properties such as topological photonics and so on. Another theme is to make light interact using matter. As we know, light doesn't talk, photons don't talk to each other, but using matter, maybe perhaps we can make them interact. And of course, we would like to do that for obvious reasons, something like this. And we can take this theme further and say we want to make interactions between light and matter so strong that you no longer can talk about light or matter. Essentially, things are now hybridized into half light, half matter states, which we call as polaritons. So that's another theme in our lab. And we do all this currently. The material of choice for us are these van der Waals materials. As we know, they come in a wide variety of properties, from semiconducting, insulating, and so on. In this talk, I'm going to focus primarily on TMDs, transition metal dichalcogenides, as we heard from the last talk as well. And in particular, I'm going to focus on selenides of moly and tungsten. Okay, so these are also layered. You can use the same Scotch tape technique to create heterostructures and so on. So what do we want to do with this? So currently, we are interested in generating on-demand quantum matter. So you want to have some kind of a 2D material, shine light, and make some interesting matter from there. And the key point here is the matter will be comprised of optical excitations, such as excitons, as your constituents. You can add electrons to the mix, but we want to see what kind of matter we can create out of equilibrium with excitons and other charged excitons as constituents. Okay, so that's the setting. And then because these things are naturally dissipative, you can understand what's happening in your matter part by looking at the light which leaks out. So this light which leaks out gives you information. This can serve as a probe of what's going on inside in terms of the interesting physics. And you can also imagine that there is a non-trivial topology of bands in this material, which will also play a role to give you perhaps even topological phases. And so the first thing you want to do with this in this setting is to have interactions which are tunable, right? So as I'll show later, you can have both repulsive and attractive interactions with this material in the optical excitation. So that's nice. You can switch the sign of the interaction. You can also create, you can also tune the quantum statistics. So you can have fermions or bosons and charged excitons, which can give even more richer phase type. Okay. And a slightly separate theme, although perhaps connected, is that because this is a two-dimensional material, if you have trapped spins or charges on the surface, you can use that as quantum sensors and get very high sensitivity. And not only you can sense the environment with this, but you can also perhaps sense a quantum matter which is sitting next to this in another 2D structure. So in an all 2D platform, you can do quantum sensing. So that brings me to the outline of today's talk. So I'm going to first give you a very quick introduction in optics of TMDs, why, in my opinion, this material is different from other semiconductors, traditional semiconductors. Then I'll talk about quantum emitters or single photon emitters in this material, and then switch to the interactions between such optical excitations. In particular, I'll give you two results. First one is about few body interaction in this dipolar excitons, where we see some kind of a quantum nonlinearity. The other result is on many body interactions, many exciton interactions, which leads to optically induced magnetic field. So you get a pseudo magnetic field without really from light. Okay. So now we have, there is another, if I get time, I'll talk about quantum sensing of correlated electronic states with these dipolar excitons. Okay. All right. So the main difference between TMD and graphene is, if you look from the top, TMD breaks inversion symmetry. So essentially the honeycomb lattice now has two different sublattice atoms. A and B are now moly and the chalcogen, or tungsten and the chalcogen. So that breaks inversion symmetry. And naively, you can say this essentially changes the spectrum from a Dirac-like dispersion into a parabolic band or hyperbolic band gap, naively. And now, because this band gap can be large, it's in fact 1 to 2 electron volt, so we can do optics with this. So this becomes an analog of graphene for doing optics. So you can imagine creating electron hole pairs across the band gap that's going to form excitons. So you might wonder, what is special about optics? Is it just like any other semiconductor? And the first thing that comes to mind is that we are really in the two-dimensional limit. And so all the excitations I'm going to generate, the electron hole pair, the Coulomb interaction between them is going to be very strong. So screening is reduced. So the Coulomb interactions are strong, and the two-body exciton that you create is going to be very tightly bound, and its binding energy turns out to be half a eV, so pretty strong, pretty large. And the Bohr radius is very small, so these things are very tightly bound. And you can also have trions, which are charge excitons, which are stable at room temperature, right? So that's the first thing. This also has implications for light matter coupling. So as you can imagine, light matter coupling is also coming from essentially Coulomb interaction. So if you do a back of the envelope calculation to figure out what's the strength of this coupling for a lambda confined light mode, you get that number, the vacuum Rabi frequency, to be about 30 milliV. So again, this is 10 times larger than gallium arsenide. And because of this, you expect very strong light matter coupling leading to polaritons, exciton polaritons. So you can have an exciton and a cavity mode, and they will anti-cross and give you these polaritons. And indeed, that's what we see. This is data taken in Atachi Mamoglu's lab at ETH, showing this is the exciton mode, and these are the different cavity modes, and they anti-cross nicely. And this number is roughly corresponding to the 30 milliV you saw before. Okay, and then since then, many groups have seen polaritons in this material. Okay, so you might say, well, everything is scaled up by a factor of 10. That's a quantitative difference. What about qualitative differences? And for that, you need to look at the band structure. And so in particular, if you look at the Brillouin zone, just like graphene, you have two valleys now. And this is where the bands come closest. This is where the low energy physics is taking place. But let's say you don't know much about this. The first thing you will say is, well, the energy is exactly the same for the two valleys. So what's different? As you know, band structure is not everything. Maybe we should look at the actual wave functions at these points. And you can do a simple tight binding model to figure out what's the wave function looking like in terms of the subatom basis. And it turns out at the valleys, at the two valleys, they are the same. They're exactly the same in this basis 1, 0, and for the other band 0, 1. So even the eigenstates are the same. So what's different? And I'm sure most of you already know the answer. You have to look around these two valleys. So if you expand close to this point, what you see is that there is a phase winding in the wave function. And that winding is opposite in the two valleys. So you get a winding of plus minus 1. So long story short, electrons in this material close to the bands are chiral. That's the key point. And this chirality translates into many interesting qualitative properties. For example, the excitons you're going to create are also going to be from K point, not gamma point. And so they will see this chirality. For example, you get an interesting magnetic moment resulting from this phase winding in Valley-Zeeman effect. You get other Berry curvature effects, which is closely tied to this phase winding. Even the excitonic spectrum gets modified by this phase winding. So you have really changes which are on the level of textbook, and also the optical selection, right? So I don't have time to get into that, but that's the key message, that this is the difference between this material and other semiconductors. And one of the first thing which people realize coming from this, using this fact of chiral electrons, is that you have valley tied to the helicity of light. So you can use this to do Valetronics, where circular polarization of light controls which valley you talk to. Okay, so you have selectivity, and you can take this and make it into from a classical bit into a quantum bit by shining linearly polarized light, for example, where you can create superposition of the two values. Okay, so that's what people try to do in the early days, and they were successful. The snag is, although the coherence time is longer than the lifetime itself is pretty short. It's on the order of picosecond for exciton. So that's not very useful. And another detail here is that there's electron hole exchange in any neutral exciton, and that's actually going to mix the valleys. So the concept of valley is gone once you go away from single particle into exciton. So you get linearly polarized mode. And this is not special to TMD. This happens in gallium arsenide as well. Okay, so to solve these two problems, for example, lifetime, what you can think of is confining the exciton. And once you do that, you increase the lifetime. Okay, so that's the first thing which we observed in these materials at low temperature, that excitons do get localized. Here, this is a photoluminescent spectrum taken at low temperature. And these are different localization spots. And you can see very sharp emission at these spots, which are coming from localized electrons. And its line width is about 40 micro eV, which is much narrower than the free exciton line width of about few millieV, 10 millieV or so. Okay, and as a result, the lifetime goes up from 1 to 10 nanoseconds. So that's the first useful thing which happened. This also gives you quantum emitters. So because this is really a two-level system, you get photons one at a time. So you get single photon emitters. So they can be useful too. You might wonder what happens to the valley degree of freedom. And again, I don't have time to get into the details, but essentially it's preserved. So the confinement is kind of gentle, that you don't mix the two valleys. The valley degree of freedom still makes sense, besides the exchange part. And since then, people have actually, so we saw these in a very uncontrollable fashion. But now, since then, people have used strain and other techniques to confine excitons in a deterministic fashion. Okay. All right. So I don't want to dwell too much on that, but one quick comment is you can also initialize single spins in this material. So you can actually have not just excitons, but charge excitons which carry excess spin. Okay, so now I move on to the main part of my talk, which is about interaction. So now we want to make these excitons interact. So the first thing which we did was to look at heterostructures, type 2 heterostructures of moly and tungsten selenide, where electron lives in moly and the hole lives in tungsten. That's coming from the type 2 band line. So now, as you can imagine, the electron hole is separated, which means you now have a permanent dipole moment, which will couple to the electric field, and you can tune its energy. But more importantly, now imagine if you have two of these in this heterostructure, the dipoles are always pointing in the same direction. So it's like having two tiny magnets which are going to repel. Okay, so this is first kind of interaction that you can imagine. So you have tunability of a single photon emitter if this guy gets localized. And you have repulsive dipole-dipole interaction, which will even make the photons interact. Okay, so we do that. We actually make a device where we have this heterobilayer, and we put it in a gated structure to apply out-of-plane electric field. And this is what we see at low temperature: sharp localized emission in the region of interlayer exciton, and you can tune its energy by electric field. Okay, so that's nice already. And you can tune its energy by over 1,000 times its line width, which is also quite attractive. Now let's come to an interaction. So what we want to do is try to put two dipoles in the same trap. And because of now the on-site repulsion, you expect that if this is the energy for 0 to 1 transition, for 1 to 2, this will be shifted by this dipole-dipole interaction. And if this shift is larger than the line width, then you are in a quantum nonlinearity regime, something like a blockade regime, where the presence of just one excitation blocks the second excitation. right? And so we naively do this by just increasing the power, and then we see a second peak. So this is the first peak. It's jittering. This is the time axis. That's typical of quantum emitters. And now at higher power, you see something at the blue side, which is higher energy. And it's also jittering exactly like this. So we know these two are in the same trap. And this shift is larger than the line width. In fact, it's about 2 millieV, which is about 200 times larger or even more than the intrinsic line width. So this is essentially the signature of quantum nonlinearity in the system. And we see this in other emitters too, other trapped emitters. And this is like a biexciton, only that it's not really a bound state. It's correlated motion of two excitons in a trap. So it has to satisfy certain power dependence, which it does. So the exciton is linear in power, but the biexciton scales almost quadratically till it hits saturation, and we see that. You can also use this biexciton for getting entangled photons. I don't think I have time for that, so let me skip that. Now, if you keep increasing the power, what we see is systematic peaks appearing on the blue side. Okay, so always at higher energy because you're repelling. So if you try to add more and more, you have to pay the penalty. And at even higher energy, we start to see some kind of a blue band. Now you can take these three peaks and try to figure out what's the arrangement of exciton in this trap. And based on the spacing of this energy levels, you can do some calculations and you figure out that this is actually consistent with what you expect for a triangular kind of arrangement. And so essentially, what we want to do now is take a trap and start loading it with lots of excitons and hope that they make a spontaneous dipolar crystal inside of this. So you can have single photon emitters in an array, but not with any lithography, but kind of self-assembly. So that can be very useful. Okay, and I must mention that other groups have also seen this, Jonathan Finley's group at Munich. Okay, so now let me talk about go from few body interactions to many body interactions. So now I'm not going to talk about trapped exciton, but imagine you have interlayer excitons which are dipolar, but you put a lot of them, and what can we expect? So here, let me give you a very, very simple picture of what one can expect. So these excitons are essentially bosons. So you can think of two repulsive bosons. So the spatial wave function likes to be antisymmetric to reduce the repulsion. The overall wave function has to be bosonic, so it must also be antisymmetric. So the lowest energy configuration is kind of antiferromagnetic for these repelling excitons. And the higher energy configuration is going to be split by some exchange energy. Right, this is the exchange interaction between the spin or values. Okay, so how can we probe this, right? So what we can do is now we really want to create this kind of an imbalance between the two spins or valleys. So if you shine with circularly polarized light, you can do that. So with circularly polarized light, you can populate one valley. Let's say with sigma plus, you can populate K valley more than minus K. So now you have an imbalance. They are still degenerate. But now the exchange interaction kicks in and lifts this degeneracy. So you basically have a magnetic field without really applying any magnetic field. So that's what's shown here. So the shifts of the energy of each exciton has a repulsive component coming from just the total population, but has an exchange component which depends on the difference of the two valleys, the imbalance. Okay, and so we do that. So we can just shine circularly polarized light. At low power, we see that the two valleys are degenerate. So two valleys are basically the two circular component of your emission. So they are degenerate at low power. As you crank up the power, you see a splitting now between the two. And if you flip the excitation polarization, the splitting flips. And you can plot the splitting as a function of power. And you see at very reasonable power of 10 microwatt or so, you get a splitting which is 4 millieV, so which is rather large. And this is CW power, so it's not pulsed, it's very low power. Essentially, what you have is with 10 microwatt, you have an effective magnetic field of 6 Tesla, right? So you just turn on this field, this laser, and you get a 6 Tesla field. And to show that this is really like a magnetic field, what you can do is you can actually apply a real magnetic field and see if these two either add or cancel. And indeed, that's what we see. You could be sitting at 6 Tesla and you shine some circularly polarized light, and you can make the splitting disappear by canceling with the exchange field, or you can enhance it. Okay, so that's pretty useful to generate magnetic field for these excitons without really cranking up 6 Tesla. Okay, how much time do I have? Maybe, okay, let me quickly talk about this, which is what I promised before, that you can now also turn the sign of the interaction. So for this, you have to make another heterostructure where you no longer have just 2 layers, you have 3 layers. So you can have moly, tungsten, moly, or tungsten, moly, tungsten. And in the first bilayer, the dipoles are pointing in one orientation, but in the second, the dipoles are pointing in the opposite orientation. And because of that, now you can have these dipoles attract each other, whereas these will repel each other. And by controlling the population of these excitons optically, you can have effectively attractive or repulsive interactions. Okay, so we do that. I'll quickly flash this slide. So we increase the power, so we can generate more excitons. And you see that these excitons, which are actually one kind of dipole, I forget top or bottom, they redshift, so that's attractive. Whereas these other dipoles blue shift, which is repulsive. And then if you turn the power back down, it goes back, right? So this is a signature, preliminary signature for tuning interactions. Okay, so what we want to do with this is kind of use this interaction and nonlinearity for Bose-Hubbard kind of physics, and also create interacting phases of photons using dipole blockade. You can think of a Wigner-like dipole crystal, or if these condense, you can think of supersolid, and so on. And you can add spin valley to the mix and get quantum magnetism. So I don't know if I have time, but do I have time for the last part, or should I just skip and take questions?
You have 10 minutes.
10 minutes?
Yes.
5 for questions. Okay, perfect. So let me quickly talk about this last part, which is, again, very recent preliminary results. Here, we want to use these dipolar excitons, trapped dipolar excitons, as quantum sensors. And what we want to sense is some correlated electron states, which might happen in this Moiré bands. So we have the same tri-layer structure here, but now we have gated device to control the electric field and also add carriers to dope it. And we are primarily interested in electron doping. So the electrons are going to live in the middle moly layer, and the excitons are going to live in the top or bottom layer. So first thing you see now is in this sample, which is different, is that the emission is much more stable. You can see this is on the order of 1 hour, and the emission is extremely stable, and also much narrower now, so 26 micro eV. So now these sharp lines can be very sensitive sensors of electric field, and in particular charges which are around. They don't jitter, so they are very stable. And you can see here, you can tune it very finely. So what we want to do is we want to load the moly layer with electrons, and those electrons are going to interact with electron-electron interaction in this Moiré almost flat band, and give you correlated electronic crystals, Wigner-like crystals, due to repulsion. And then we want to use the exciton to probe these electronic states, these crystalline states. Okay, just a quick comment, these excitons are also very nice magnetic field sensors, not only electric field, but magnetic field. For example, the circular polarization of these emitters sharply rises from 0 to almost 100% in a 6 millitesla window. So you can measure down to millitesla. Anyway, so let's now load this structure with electrons. So initially you have these stable sharp lines, and as you load these stable sharp lines starts to jump. You see this very jumpy behavior, lots of jumps as you add electrons. But the main point here is that if you sweep back the gate voltage, so I'm adding electrons here, and then here I'm going back to the stable region, you can see that this chaotic pattern is actually very deterministic. All these features are like mirror image about this line. So these are perfectly well reproduced. So these are not random. These are, these are deterministic with gate voltage, even the finest feature that you can find. And you can correlate this with the reflectance of intralayer exciton. And although in the reflectance, you don't see very sharp jumps, what you see are some global features. For example, here you have the intrinsic region of exciton. This is the 2s peak, and this is the tungsten exciton. This is the moly exciton, also shown here. And this is a voltage where suddenly you see a kink in the reflectance for both moly and tungsten. So if you assign this voltage range, this from as the intrinsic to be 0 and this kink to be 1 in some units, and then plot the fractions of this voltage, just relabel this axis, what you see is something very interesting. So these are your sharp lines. They start jumping here. And what you see is if I plot this in fractions of 1/12, many of the jumps, several jumps, fall nicely on these 1/12 lines. So they are now correlated, and they are not random jumps. They're happening at certain fractions. And the ones which don't lie on these fractions still maintain some kind of a rule such that if you look from this jump to another jump, which is also not falling on this 1/12, this length is still 1 in the units of nu equal to 1 or 1/3 and so on. So you can do a statistics of this and look at where the jumps are taking place in units of 1/12, fractions of 1/12, and you see a clear peak at 0, which means most jumps fall on this 1/12 graduations. The ones which don't, residual peaks here, are actually also lying on half or 1/3 of 1/12, so which are also good fractions. And this we can do for over 300 jumps. So essentially, this is an indication that we are seeing the crystalline electronic crystals, which are formed at these fillings through the jumps of your emitter. Okay, you can do some simulations. You can calculate the Moiré lattice, try filling the lattice, get these electronic crystals just from classical Monte Carlo-like simulation. Place your quantum emitter here and see how much will it shift. And this is what you see. This is a simulation, and this is the real data. And you see qualitatively, it makes sense. There are both red and blue jumps, and there's an overall blue jump, overall blue shift, which is what's also captured in the simulation. All right. So, and here we can also estimate what's the Moiré length from the scale, from the size of the jump. But I think I'm out of time. So thank you for your attention, and I'll be happy to take any questions.
Thank you very much for the wonderful talk. And time for the questions. Do you have questions in the audience? Or chat, probably? No? Okay, one question in the audience.
Yes.
Thanks for the talk. I found it quite interesting.
Thank you.
I was surprised when you said that in the first part that you're able to observe the triangular lattice formed by the excitons. But this usually is push out the reflectance. And I come from the ultrapolar gases community, and I work with bipolar gases in the past. And usually this crystallization is completely out of the experimental regime. Have you
actually, so you're talking about
at which density it occurs?
You're talking about this arrangement of triangular, right?
Yes.
So
Yes.
actually, for this is not a crystal just yet. It's just 3 particles, right? So it's in a trap. If you actually do the analysis for many excitons in a trap, you can do the number. So here, what's as you know, coming from EMO community, what you need to calculate is some kind of a ratio between kinetic and in kinetic and potential energy. And you're right, in 2D, it's going to be very hard. It's not possible. But in 1D, so you can create some kind of a Tong-Girardot kind of situation, or a dipolar crystal in 1D. There, the numbers are actually promising, so you can do that. In 2D, you're right, it's going to be a struggle, unless you have other tricks up your sleeve.
Thanks. Very interesting.
One more question in the audience.
Hi, thanks for this wonderful talk. Very interesting. So regarding these very narrow lines, so a few years ago, there were quite some publications about more excitons.
About, sorry,
kind
what?
of observations, no, like either narrow lines or having only few lines that are not narrow at all. So this seems to be quite deterministically what you can prepare here now. So is there any recommendation how you yield the narrow lines?
Right. So actually, now we have a few samples which show this. So, but we don't know which one factor leads to this. I can tell you what all we changed. So we have moved from this usual technique of PDMS to PPC pickup, which is always cleaner. So the flakes are never seeing anything else other than boron nitride, which is cleaner. But I think another important thing is we have a very large top and bottom graphene gate and a thick BN. So this graphene gate is going to screen out any charge fluctuations that you might have and give you sharp, stable lines. We have also played with the thickness of HBN. Seems like we don't need super thick. In this case, it was 300 nanometer, but perhaps it will be fine with thinner as well. But I think this large graphene gates are helping to reduce the charge fluctuation. That's my guess. Or perhaps it's a combination of sample preparation and that and this. Does that answer your question?
More questions? So then let's thank speaker again.
Thank you very much.
And now we will have a short break, 10 minutes, and we will come back in 5 minutes to 7. So yeah, see you soon.
Hello, 1, 2, 3, 4.
Let's wait a couple of minutes.
I'm fine.
I will stand up like 5 minutes.
Okay, so I should stop.
I mean, if you want, like up to you. How many times do you want for a question? good afternoon, everyone. Oh, good evening, sorry, everyone. And we now have the last session of today's talks. So the next speaker is Jean-Marie Pomerol with a talk which is entitled "Unveiling the Optical Emission Channels of Monolayer Semiconductors Coupled to Silicon Nanotubes." So the stage is yours.
Thank you. Good evening. So thank you to the organizer to allow me to present this work, which is made in CMS laboratory in Toulouse. So just across the Pyrenees, in fact. So it made me one of the lucky ones that could come here and talk in person, which I must say it's been a long time and it's nice. So this work is concern the coupling between nano antennas that carry Mi resonances with TMD monolayers. So to give you like a brief introduction on the high refractive index nanostructure, so this is made of a dielectric nanoresonator with high reflective index. In our case, it will be silicium, and they're able to support Mi resonances. So these resonances are based on displacement current. So if you have a rotating electric field in your particle, you will have a magnetic dipole that will appear. And if you have a rotating magnetic field, you will have an electric dipole in your system. And this type of structure have been shown to strongly enhance light scatter, to be able to shape the emission of the light. So if you see these three particles with different size that scatter light in a different region area of the visible light, you can also have a unidirectional scattering through Kerr effect, for example, or 1D or 2D propagation over long distances. So this type of structure can be tuned over a large frequency range if you change the index of the material and the resonator shape and size. So if we compare to the other non-system to control light at sub-wavelength dimension, which would be a plasmonic system like in gold dimmer, what are the main differences? That in a plasmonic system, you will have a lot of absorptive losses. So it means lower heating. For the silicon dimmer, everything takes place into the scattering. So lower heating in this type of system. The other main difference is that I told you, you can have a magnetic dipole with Mi resonances. So you can locally enhance the magnetic field. And this could be used to work with magnetic transition, for example, in rare earth. So this is some work we've done on this type of structure. And this is also a versatile route for fabrication because it's compatible with CMOS technology. Okay, so if we couple this system with monolayer TMD, there is some work already done in this type of structure, and you can have several phenomena that take place, like for example, directional emission. So if you put silicon nanowire on top of MOS2 monolayer, the PL of the MOS2 will interact with the Mi mode in the wire and be scattered in one direction, preferentially from top compared to bottom. You can also have the Mi enhanced photoluminescence of your layer, within this case, for example, GAP dimmer, which enhances 50 times the amplitude of the photoluminescence in WSE2. But as we've seen in the previous talk, there is also some other effects which are not linked to the electromagnetic properties of the antennas, but really the physical properties. So if you put a flake on top of antennas, you will strain locally the flake, which will decrease the gap, and through exciton drift, you may enhance the photoluminescence locally, like in this case. So in this system, this type of system, all of these three phenomena will always be come together and intertwine. So the idea of this work was to really try to disentangle the different processes responsible for the PL enhancement. And we came with the idea to compare a conformal system when the layer is deposited on top of the antennas and the antennas over the substrate, so it will be deformed by the antenna, and to compare it with a planarized system when the antenna are buried inside the substrate and the TMD layer is deposited on the top and is not deformed at all. We also chose asymmetric structure that will show very strong polarization dependence that will only be linked to an antenna effect. We designed different size of resonator to be able to tune the mirror resonance, of course, and work with two TMD, tungsten diselenide and aluminum diselenide, which showed slightly different band structure. So in this talk, I will, for question of time, only talk about the difference between conformal and planary system for WSC2, show you some numerical simulation to explain the results. I conclude, and if I have a bit of time, I will talk about some perspective about focus cylindrical vector beam. So this is what the array look like. All of the antenna have the same shape, so they are a dimmer of silicium. All of them have the same height and width, and what change is the length of the silicon and the gap between the two silicon square. You see in these dark field images that already you can see some difference in the way they scatter the light, with red here, red orange to green, and here is the scattering cross section for 4 selected antennas to show you how it moved. Now, what we did is through dry transfer method, we deposit the TMD on top and cover it with boron nitride. This is the IFM images to show that the TMD layer is quite conformal to the antennas. So this is WSE2. We worked at laser excitation of 532, so far from the exciton energy. So we excite electron pair at very high energy compared to the PL. And this is the integrated PL map for two polarization parallel to the long axis of the antennas and perpendicular to the long axis of the antenna. So first thing that comes to the eye is that for some of the antennas, there is a very strong PL enhancement, one of magnitude nearly for those. And also there is a strong polarization dependence with some antennas that can be completely turned off by turning the polarization of 90 degrees. So in more detail, I will focus on this antenna. In black is the normalized scattering. We see that we chose this one because one of the resonance corresponds to the excitation energy, and the scattering is very close for MOS2 and WSC2 on this one. So this is just a zoom. And if we look at the shape of the PL at 3 different points on this map, here, here, and here, we see that it's very different, not only in the amplitude, but also the shape is quite different. So to try to quantify a bit more of this phenomenon, we fitted this experimental curve using 3 Lorentzian, one corresponding to the free exciton, one corresponding to a trion, and the last one to the dark out of plane exciton. So this is the 3 main peak we expect for WSC2 at room temperature. And we can now follow along this line amplitude and the PL energy of all these 3 main peak. What we see here is that over the antenna, there is a clear decrease in energy of the emission for the free peak, meaning that there is a gap reduction at this position. So this is a clear signature that there is strain, of course, in this system, a tensile strain. and this is also confirmed by a Raman spectroscopy, where we see a shift in the Raman peak. So this means in this system there is excitonic drift that will take place, and there may be some antenna effect, but it will be hard to distinguish one from the other. The also interesting thing that we see is that if we look at the edge of the antenna, the amplitude of the red Lorentzian corresponding to the dark out of plane exciton is very strongly enhanced. And that's interesting because the dark exciton dipoles stick out of the plane, so the emission should be in the plane. So this is a forbidden state. It's dark. So there is something interesting to look at in this, and I will come later to this during the simulation. So now we turn the polarization, and the PL map is completely different. You see the PL enhancement is now time 3 versus time 8 previously, and the maximum is located in between the antenna and not all over the antenna like in the previous polarization. So this is not a surprise. In fact, it's made by design, because if we calculate the near field intensity map of the electric field at 532 nanometers, we see that we expect the electric field to be strongly enhanced in the parallel case and close to zero enhancement in the perpendicular case. So here we are, the idea was to affect the efficiency of the electron hole pair creation process by decreasing the field in this case, and that's what we see. So this is interesting. This is a pure antenna effect. It's not linked to strain at all. And if we look again with the same procedure at the PL shape and amplitude, we see here that there is no observable energy shift of the exciton line, so meaning no exciton drift will appear in this system. And we see also that there is no change. All the 3 peaks are moving, changing amplification in the same way over the antenna, so there is no exaltation of the out of plane exciton. And that tells us that the phenomenon we observed previously for this dark exciton is probably linked to the radiation pattern of the antenna from near field to far field. Okay, so let's switch now to the planarized case. So we just deposited HSQ resist over the antenna that filled all the gap, and again the HBN and the TMD deposits. We see that the IFM profile is completely different with a much reduced height, and there is no TMD which is suspended now. It's all resting on the HSQ, and that's reduced the stress. There is no observable Raman shift in the system compared to previously where there were a strong Raman shift. And so we are expecting here to get a pure antenna effect. So what we see again in the parallel case, we see exaltation of the PL over the antenna is nearly 100% PL enhancement. It doubled the intensity. The hotspots are localized here over the antenna, and there is no observable redshift or change in the shape of the PL spectra. If we rotate the polarization 90 degrees, we see again that the PL exaltation is now very weak, like 30%. The hotspots are localized in between both antennae and on the side. There is no redshift of the PL and no change in the shape. So as we were expecting, now we only see an effect which is linked to the Mi exaltation of the electric field at the laser excitation. So this is interesting because when we looked at how the PL excitation were changing between vertical and horizontal polarization in the suspended case, and in this case, we were expecting a stronger effect of the Mi mere resonance. But in fact, here what happened is that when we put the HSQ over the antenna, we decrease the dielectric contrast. So HSQ have a higher dielectric index than air. So we made the performance, we decreased the performance of the antenna on this system by trying to remove completely the strain. So now let's go to this last point of this paper, is trying to understand the emission mechanism that make the dark exciton more visible at the edge. So we made simulation considering a single oscillating dipole, with an out-of-plane orientation for the dark exciton and an in-plane orientation for the bright exciton. And we move this dipole all over the surface of our antenna and calculate the far-field radiation emitted by the dipole at the PL wavelengths. And we move this dipole following the flake geometry, because on the edge there, but also on the lateral structure, as is conformal, it changed shape. And this is the emission pattern calculated at some specific point on this antenna. So everything that will be inside the dashed line will be captured by our objective. So what we see is that if we put the dark exciton dipole at the edge of the structure, most of the light emitted by this dipole will be redirected by the antenna toward the top and captured by our experimental setup. But if we do the same thing at the other edge, on the side, we see that it's much less efficient. So that's explain why this dark exciton exaltation will only appear on the top edge here and here of this antenna, and not on the side. Now, if we look at the same thing and compare bright exciton and dark exciton right in the middle of the antenna, we see that what the objective will see is mainly the bright exciton. So we do not expect any exaltation of the dark exciton in between both antennas. So this is quite good compared to what we see experimentally. And we did the same thing, of course, for the planarized system, and nowhere we were able to see that the dark exciton coupled with the antenna could be increased in amplitude. So there, on this case, we were not expecting this effect, and that's what we see. Okay. So to conclude, we see a strong PL enhancement for the WSC2 and also the MOSC2, not shown here, on the non-planarized resonator. It's a combined effect, of course, of the out-of-plane dipole emission, strain, and the me-mediated enhancement of the electron hole pair at the excitation. Even on strain sample, we are able to control the emission using a light polarization with we can turn on and off the enhancement. Let's say for some antennas it's more effective than for others, of course. On the planarized nanoresonator, they are strain free, and the PL is only emitted through the me resonances, but it's quite weak. And as I said to you previously, it's linked to the dielectric constants contrast that is decreased. So it seems that I have still some time, so I will talk a bit about some perspective on further engineering the near field coupling with TMD. So as you've seen, the direction and the amplitude of the electrical field is like critical in this system. So we decide to work with a focused cylindrical vector beam coupled with this dielectric nanoparticle. So two of the spectral beams that we use are the radial configuration, where the electric field stick out of. So the electric field is oriented all this way on the beam, but when you focus it, you will make an electric field sticking out of your plane when you're shining from the top. And from the azimuthal, this is a rotating electric field, so it's the magnetic field that will stick out. Now, if we shine this type of beam on a silicon nanoparticle, here is what happened for the Gaussian beam, the one we used previously. So the electric field is coming this way. The light is shining from the top, it's coming this way. So you have an electric dipole in your particle this way, and the magnetic field is rotating around. But with the radial beam, as the electric field is, the beam is coming this way, as the electric field is oscillating like this, you have the electric field oscillating from along your beam direction, and the magnetic field is rotating this way. And the azimuthal is or the opposite, is the magnetic field, which is oscillating vertically, and the electric field around. So now if you shine, if you shine this type of beam on an antennas, you will have completely different position of your electric or hotspots. So the exaltation of the electric field will take place at very different position. And I'm out of time, so okay, I will thank you for your attention, and thanks all the collaboration that work with me on this.
Thank you for the beautiful talk. Yes, and now time for the questions. So, one question in the audience.
Thank you, Jean-Marie, for a very nice talk. So I have a very short technical question where you show the exciton shift versus the x coordinate along this antenna. So what is the step size? It's about like a few hundreds of nanometers.
200 nanometers.
Okay.
And in all the map is 200 nanometers.
And it's defined by the spot size of the laser beam, yeah?
Yeah, we use a beam expander at the back of the objective to try to reduce the spot size as much as we could, but it's around 500 nanometers. Yeah. But okay, you know, most of the energy on a Gaussian beam is in the center. So, but 200 nanometers, it's really like the maximum resolution we can expect.
Maybe it would be nice to try to probe this field with maybe thirsty enhanced.
Yeah, we tried, but that left a new problem, is that on the planarized system is fine, it's very easy, but on a non-planarized system, this is they are quite high. High antenna is 100 nanometers. So we have some artifacts when we compare both that come from the fact that the tip is feeling the edge of the antenna before. So yeah, we are working on this. Yeah, I'm sure it will reveal a lot of things.
Okay, thank you.
Okay, do we have more questions? Yes.
Hi, thanks a lot. Actually, two questions. It looks like the dimer in the non-planarized emits like with one lobe, and then in the planarized you get two lobes.
Yeah.
Is that because it's acting like two monomers? Or?
You mean here is one lobe?
Yeah.
And yeah, is because this is linked to, is like dominated by the strain. So in fact is linked to this question, is that when you shine light on your sample, you have a beam that is 500 nanometers to 1 micron, and all the excitons which are excited in this beam will drift toward your maximum strain part, and it will become very, very bright. But yeah, in this case there is no drift, so it's really and in fact it's quite hard to simulate this, because this is a raster scan, so we need to take each point into consideration and sum everything that take place for each point.
Okay, so in this case, is the dimer acting like together or each
Yes.
antenna?
Yeah. In fact, they are acting together more efficiently on this one, because when you have your laser beam inside this gap, yeah, even if the oscillating electric field will be this direction, they will communicate quite strongly and hence the PL there, the electric field.
Okay, thanks.
Okay, let's thank our speaker again. Metamaterials with direct carriers for nonlinear terahertz photonics. So please, this is yours.
Yep, good afternoon. I hope everybody can hear me. So the idea of this talk, well, first of all, thank you all for still being here at this very late hour. So I see some people here in the audience, some people online. So I'm very happy you're still here. So at this conference, we've seen a lot of photonics, a lot of 2D materials. We've also seen a bit of terahertz and a bit of nonlinear photonics. So the idea in this talk is to combine all these aspects in a mix that I think will hopefully convince you that this is a very interesting combination of using 2D materials, in particular for nonlinear photonics in the terahertz regime. So before I will talk about this, I have to thank my co-workers. So there's people at ICN2 who were mainly there for sample fabrication. Then most of the experiments were done in Dresden at a linear accelerator. So those are the people listed here in the middle. We also had some samples and collaborations with the people at ICFO, Barcelona. And also a lot of this work has come about from a collaboration with the group of Dimitri Turguinovic, who's now in Bielefeld, Germany. So I will go through this very quickly. This is for the non-experts student in the room. So of course, if you have a material and you come with a low intensity light, so you come in with a certain frequency. If you look after the material, you have light with the same frequency. Typically, it's a bit less intense. That is because you create a polarization in the material which follows this electric field. And this is governed by the linear susceptibility. This is a complex constant. And it basically includes both absorption and refraction all in this single constant. Now, what happens if you start increasing more and more the incident light field? At some point, the polarization inside the material cannot follow anymore this electric field strength. So it's not linear anymore in electric field, the amount of polarization that you're creating. So you can do a Taylor expansion, which shows you that you also get terms that are going with electric field to the power 2 or 3 or 4 and so forth. Now, as you probably know from your trigonometry classes, if you come with a sine wave with a frequency f, but you also have a component that is the sine wave with the frequency f times a sine wave with frequency f, you also get components with the frequency f minus f, so a DC component, and also with double the frequency. So this is something that's typically used to create second harmonic. We saw a little bit in the previous talk. This is a picture that I got from the internet where you very clearly see that if you have a nonlinear material, you come with enough intensity, you shine red light, and you double it into blue light. So you can generate harmonics. So this works really nicely in the visible regime and is very useful for all kinds of applications. I list a few here. But it's actually very difficult to do this in the terahertz regime. So there's not a lot of good materials that can do efficient nonlinear optics in the terahertz regime. So the terahertz regime is where you have a wavelength of 300 microns. So it's very long wavelength, very low energy. And it's a bit located in between the electronics regime and the optics regime. So that can be also an advantage because you can use tools both from electronics and from optics for this terahertz regime. It's also a very interesting regime for all kinds of applications, ranging from security, quality inspection, and diagnostics, all the way up to data communication. So the terahertz regime is very, very interesting. And we were struggling to find good materials to do nonlinear optics in the terahertz regime until we met our 2D materials, and in particular materials that have Dirac electrons. So electrons with a linear momentum energy dispersion relation. So of course, we know several of those materials. The most famous one, arguably, is graphene, which is a layered 2D bonded material, 1 atom thick. There's also topological insulators, such as bismuth telluride, where in the unit cell you actually have 5 layers, but it's still a layered material because most of the bonds or all the real bonds are in plane. And these materials have a small band gap, and within the band gap, there are surface states with linear dispersion relation. Now, there's also 3D bonded materials, such as cadmium arsenide, which are well semi-metals. They're 3D bonded, they're non-layered materials, but they also have certain situations where you get linear dispersion relations. And now it turns out that in the very last few years, people have observed very strong nonlinear effects in the terahertz regime in all these systems. So both in graphene, in TIs, and in well semi-metals, people have shown terahertz harmonic generation, for instance. I show a few of these references here. So we've been involved mostly with the graphene terahertz harmonics. I will show you a little bit more about this. So the way this works is that you come with a relatively high intensity terahertz field. So I say it's high intensity for being a terahertz pulse. It's actually very low field strength if you compare it to what people use in the visible. So in the visible, it's quite easy to get megavolts per centimeter, or even gigavolts per centimeter. Here, our peak is on the order of a few tens of kilovolt per centimeter. So it's much less intense than in the visible, but for being terahertz pulses, which are not as easy to generate as visible light, they're actually quite intense. We shine this onto our graphene, and then we look what happens in the graphene. So what happens in the graphene is that you absorb this terahertz light. This heats up charges in the graphene, so this Fermi-Dirac distribution broadens. What happens then is because of this terahertz-induced broadening of the Fermi-Dirac distribution, you get actually less absorption because the conductivity in the hot state is lower than the conductivity in the cold state. So you're reducing the absorption while you're shining light on it. So that is the nonlinearity as I explained to you in the beginning. So we have this nonlinear effect, and it's related to hot carriers. So very briefly about these hot carriers. As I said, in the cold state, you have a certain Fermi-Dirac distribution broadened by, let's say, 300 Kelvin if you do this at room temperature. Then if you heat up the system by absorbing light, so this can be light of any wavelength, from the UV, visible, infrared, microwave, terahertz, whatever you like. In the end, all that energy is absorbed in the graphene, and all the electrons are sharing this energy, which happens in a very fast time scale on the order of tens of femtoseconds. And after that, you have this broadened situation with a increased electron temperature. If you want to know more about these hot carriers, I would like to show you that we now have recently published the first review article on hot carriers in graphene in this Nanoscale emerging investigator article. So again, this happens for any kind of light that you absorb in your graphene. You get these broadened Fermi-Dirac distribution. And in the case of graphene and incident terahertz light, I'll show you some former results we obtained a few years ago, where if you use relatively low intensity of your terahertz light, you get an absorption of, say, 10–12%. That's just your free charges that are being accelerated by the terahertz pulse. That's your typical Drude absorption. Then if you keep increasing your electric field strength, you absorb less and less. So this is a saturable absorption effect, which is a nonlinearity caused by the fact that in this hot state, your conductivity is lower. And if your conductivity is lower, you absorb less terahertz light. So we can now go back to our situation where we have this intense terahertz field incident on our graphene. We then put a filter behind the graphene, which we use to filter out the fundamental. And then we look what is left. And what we see is a very fast oscillation. It oscillates 3 times faster than the fundamental. So this is actually a third harmonic signal generated by this nonlinear polarization response in the graphene. And I should point out that both these signals I'm showing here are actually measured. So because it's terahertz fields, we can actually resolve them in time and not the intensity, but the actual electric field. So we really see the whole oscillating wave here at 3 times the frequency. And you see the intensity is quite high. So we come in with 80 kilovolts per centimeter, and we get a third harmonic close to 400 volts per centimeter. So that's quite a high efficiency. And in that first paper, we showed that we can do this not only for the third harmonic, but also for the 5th and 7th harmonic. So the even harmonics are not allowed because of symmetry reasons, but all the odd harmonics are allowed. And we were able to resolve them up to the 7th harmonic in those first experiments done in Dresden. So we expected a nonlinearity, the third order susceptibility of 10 to the minus 9 meters squared per volt squared, which is actually a really high number. And third harmonic conversion efficiency on the order of a few tenths of a percent. So just to put this in perspective, if you compare this to work that was published around the same time in the visible regime. So in the visible regime, people also saw very nice third harmonics. And what's very nice is that they're also very tunable through the Fermi energy. But their nonlinearity was 9 orders of magnitude lower than the one we find in the terahertz regime. And the reason for this is that in the terahertz regime, your hot carriers, this electron thermalization, is enabling this terahertz harmonic generation. Whereas in the visible regime, it's actually working against the harmonic generation. So because of all this thermalization, everything broadens and you get actually a lower efficiency in your nonlinear generation than you would without thermalization. Okay, so this is all very nice. We get good numbers, but of course it's only an atomically thick or thin material. So overall, even though you have this really high nonlinear susceptibility, with so little material, one can argue that you're not generating that much real harmonic signal. So one way to improve this is, of course, to use many layers, but then you need to isolate those layers, and you can use a much more clever trick, which is using photonics. So with photonics, you can actually get field enhancement and therefore have stronger interaction between your incident light and the material. And then because what you're looking at is a nonlinear effect, it's enhanced in a nonlinear fashion. So I will show you how this works. So first I will show you that it works. So I compare here a region of the sample where we just have graphene. Here we come with a relatively low intensity. So we have on the order of 20 kilovolt per centimeter incident field. So after the sample without the grating, okay, if you look very carefully, you might see a bit of an oscillation. If you look at the Fourier spectrum, you see a small amount of third harmonic. Now, if you use the same incident field strength, but we look on the grating region, you very clearly see the third harmonic and a very clear peak at the third harmonic frequency. So what happens is that in this grating graphene metamaterial, where we have these metallic gratings deposited on top of graphene, isolated by a very thin layer of aluminum oxide, you see that you get a very strong enhancement of your nonlinear susceptibility. So it's enhanced by around a factor 40, which means that now we have a nonlinear susceptibility on the order of 10 to the minus 8 meters squared per volt squared. And this also tells you that the amount of third harmonic power is enhanced by the square of this. So by more than 3 orders of magnitude. So that's a very strong amount of harmonic that we're generating thanks to this, this grating metamaterial. So again, this means that you can also get quite high field conversion efficiency, which I show here. So this is a measurement without any filters. So you see both the fundamental, in this case at 300 gigahertz, and the harmonic at 900 gigahertz. And this is for an input field of only around 30 kilovolt per centimeter, which actually you don't need a linear accelerator to do this. We actually did this with a laser-based source. And you get actually a 1% conversion efficiency in the system. Now, very quickly for the photonics guys. So of course, we also check that if you change the orientation of the polarization with respect to the grating, this field enhancement disappears. So also your strong harmonic generation disappears. In fact, at some point, your grating acts as a filter of both incident and transmitted radiation. So it stops generating any third harmonic. You can also play around with the duty cycle, which is basically the amount of metal on your sample. So the higher the duty cycle, the smaller your gap. So the more field enhancement you get, and you see indeed that you get more harmonic generation, the smaller this gap. We looked at this in a little bit more detail using RCWA simulations. This was done by David Alcaraz at ICFO. So he showed that you're not actually enhancing that much the actual terahertz absorption by putting this grating. You can see here without or with a very low duty cycle, you have maybe 30% absorption at a Fermi energy of 0.2 eV, whereas with 90%, you have maybe 40 or 50% absorption. However, you're absorbing all this light in this very small region in the gap. So that means that you actually have a quite strong field enhancement. In this case, it's a factor 5. So it's, for photonics people, probably quite a modest field enhancement. But it's good enough to get more than 3 orders of magnitude more third harmonic power generated by adding this grating onto the graphene. And that is because your harmonic is increased by more than just this factor 5. In fact, we can understand how much it is increased. And that is actually the field enhancement factor to the power of your harmonic. And then if you think about actually not the electric field enhancement, but the third harmonic power that is generated, it's actually the field enhancement to the power 2 times the harmonic order. So for the third harmonic, this would be 5 to the power 6. And then you have to take into account the fact that not all your sample is radiating. It's only radiating from the gap. So you have to multiply it by 1 minus the duty cycle. So in case of 90% metal coverage, you have to do 5 to the power 6 times 10%, and you get around 1500. The field, instead of power, if you look at the field third harmonic enhancement, that's the square root of 1500. So it's around 40. So that's all consistent with what we were seeing experimentally as well. So what this also predicts is that if you then go to even higher harmonics, so not to the third harmonic, but to the 5th or 7th or even higher harmonic, you're enhancing even more compared with the sample with the grating compared to the sample without the grating. So here you see, for instance, a simulation that predicts that for the 9th harmonic, it's many orders of magnitude more harmonic that you're generating due to the grating. And we tested this experimentally. So we have here a measurement where we use quite low incident field strength, and you see a very clear signal of the 7th harmonic. And if you want to see it, you can even see some signatures of the 9th harmonic. And again, this is for quite low incident field strength. So this is for 30 kilovolt per centimeter, generating a 9th harmonic. So people have done high harmonics, but typically it's megavolts per centimeter. Here it's just a few tenths of kilovolts per centimeter. So we thought that was quite an impressive result. So just to flash this very quickly, you can also tune this electrically by gating the graphene, thereby changing the Fermi energy. And we've shown that both for the 3rd, the 5th, and the 7th harmonic, that you can change it by almost an order of magnitude, the amount of harmonic that you can generate. So we have quite a nice toolbox with this graphene, especially together with this grating, where we have this metamaterial, where we can generate harmonics, we can tune the harmonics, and we have very large efficiencies of harmonic generation. So if I have a few more minutes left, I assume the chairman will interrupt me if I don't. I would like to show you that there's still one small issue with all this terahertz nonlinear photonics based on 2D materials, especially in the case of graphene, which is that if you keep increasing the incident field in order to get more and more harmonic generation, at some point it doesn't work so well anymore. There's a very strong saturation effect. So in fact, at some point your grating is not enhancing anymore at all the amount of third harmonic that you're generating. And that has to do with the fact that for strong incident field, there's more and more heat generated in your graphene, and that heat cannot go anywhere. So you get a lot of long-lived heat, both in the electronic and the phononic system in graphene, and that is bad for generating harmonics. You need it to cool down fast enough so that it can follow the incident terahertz electric field to actually generate the harmonic. However, as you remember from the introduction, we have these other 2D materials with Dirac fermions. In particular, we have these TIs. So what we did is we also looked a little bit into what we can do with these TIs. And the first thing we checked is, what about the carrier dynamics in these TIs? And people have already studied this, especially for bulk doped TIs. So bismuth selenide and bismuth telluride, where one is valence band doped and the other one has the Fermi energy in the conduction band. And you see quite long-lived signals. You also see in the case of the telluride some phonon coherent oscillations. But these charges are quite long-lived. And that is because in this case, you're also generating charges from the bulk. Now, if you use a tertiary mixture where you have also both the selenides and the tellurides and also some antimony mixed into it, you get actually a sample where the Fermi energy is in the gap. So that means you have no valence band doping, you don't have conduction band doping, but you only have some charges in these non-trivial surface states. And what you see then is if you excite with terahertz light and you probe with optical light, you see a very short-lived signal. That's this blue curve here at the bottom. So it lives for a few hundred femtoseconds at most. And that is because in this case, you're really probing the dynamics purely of the surface states, because you're not exciting bulk states, because your Fermi energy is in the gap, and you're exciting with very low energy with your terahertz light. So this looks very promising, because this is exactly what we want. We want short-lived hot electrons in our Dirac states. So does that mean we also get less harmonic saturation? Luckily, the answer is yes. So we compare here graphene with our TIs. You see graphene as a function of fundamental field strength, strongly saturating at some point. In fact, it never has a power dependence of power 3, which is what you would expect. It's always a bit lower because it's already saturating even for low field strength. Whereas the TIs are perfectly third order, so no saturation visible. It's still not as high as graphene, but we're working on this. And so this was published very recently. But we also have some unpublished data that I just want to flash here, where we combine our very nice gratings that enhance this light matter interaction now in the case of the TIs. And what you see now is that if you compare now graphene with and without the grating, what happens is just the curve shifts to the left, because with a lower field strength, you already have more harmonics, but then it saturates at the same level. Whereas for the TI, you actually also shifted to the left, and with the grating, you can actually get for relatively low field strength, very large third harmonic signal, even larger than graphene. So in fact, we estimate field conversion efficiencies for the third harmonic in excess of 10%. So more than 10% of your incident electric field strength is converted into a third harmonic. So with that, I would like to show you the summary with everything I told you about, so that we can generate a very efficient harmonics using Dirac carriers, both in graphene and TIs. We can enhance this using this photonic trick with the grating, and we get a nonlinear susceptibilities on the order of 10 to the minus 8, or if you prefer ESU units, it's on the order of 20, and more than 1 or even 10% field conversion efficiency. And I list here also some of the relevant papers that we published also all quite recently. So with that, I would like to thank you for your attention.
Thank you very much for the wonderful talk. Short question for me. Could you please show the data with the metamaterials and graphene, with the metal grating, with the, when you show the ninth harmonic? This one, yes. I just wondering that why the third harmonic looks lower than fifth and seventh one.
That's because we have injected here 2 high-pass filters. So we're filtering a lot of light below 1.4 terahertz with the first filter, and then with the second filter, we're also filtering below 2.2 terahertz. So basically, both the fundamental and the third harmonic are decreased by more than 4 orders of magnitude by these 2 filters.
Okay, I see. Thank you very much. And let's thanks our speaker again. That's all for today. Thank you.